This conference will now be recorded.
Okay, so welcome to everyone. Maybe I will combine the disclosure with a few sentences about myself. So I'm a biologist by training. I joined AbbVie 2012 as a trainee for drug development. And in the following years, I moved in the direction of lab automation. And then, as you see in the further talk, we realize, or I realized that if you want to automate, you also need to optimize and try to automate where possible the data integrity. That is, of course, an essential part in our area. And that will be then the kind of introduction that I will give. So Christoph mentioned already the quality by design principles that led the way of our journey. So then I will tell a little bit about our workflow standardization, the miniaturization that we did, and the automation at the end. And the next topic would be then, which is the biggest part of all, the data handling and what the automation means to the data integrity strategy that we developed. And then at the end, I will give an outlook about, we call it intelligent automation, leveraging then fancy things like machine learning, predictive analytics for the automation itself. And at the end, I will give a short summary. So let's start with the introduction. So we are located in the biologics area, and the biologics area is changing quite a bit the last years, and that results in really a heterogeneous group of different molecule formats. You see on the lower part of the slide a few examples. In the past, we just had the monoclonal antibody most left, but now we have several dozens of molecule formats. And of course, you can imagine that the stability of the drug product at the end or during the drug product development is really a hurdle, especially as we really have limited prior knowledge for these new empowered molecules and molecule formats. Of course, we have a lot of knowledge about the monoclonal antibody, but a lot of things that we learned there are not particularly true for the other formats. We are developing the liquid formulation. So how would you phrase that? Kind of the composition, the recipe of the liquid in which the biologic is stored and administered, and of course in which it is stable. So the liquid formulation contains several ingredients, and of course they need to be defined and tested in different conditions before you really have the final composition. And at the end, everything should go into either a pre-filled syringe or an auto-injector, as the common self-administration at home is state of the art for numerous indications. So that is more or less the expectation of the patient. That was the short introduction. Coming to the quality by design. So our workflow is implemented on the automation, on an automation line, as you can see here. And the idea behind were quality by design methods. And we had there simple things like the pH, but also more complex UHPLC liquid chromatography methods, as you see here, the SEC, the KEX, and the HIC. And for this, we have these UHPLC systems, which you can see on the right side of the automation line. If one wants to kind of group the instruments, you would have simple instruments for the liquid handling and the plate handling. So we have all samples in 96 or 384 well plates. So we have on the top and the lower end on the left side liquid handling systems that do the preparation of the different formulation compositions. Then kind of simple instruments that would handle the centrifugation, sealing, desealing, these kind of things. And then we have several stress conditions. And those stress are a freeze-thaw device, freeze-thaw cycles, mechanical stress shakers here, and temperature incubation for thermal stability. So kind of the stress instruments. And the third group would be the analytical instruments. And as I pointed out, the major analytic is the UHPLC. And beside that, we have a DSF instrument and a qPCR for, as I said, DSF, and a plate reader for various methods. I have to admit that we are at the moment at the end of our transition phase. So we have some instruments that we use manually, and we have some parts of our workflow that is already automated. Maybe some already saw that we have this line here in between, and that is a robot that connects all the different instruments. And the idea here is having a fully integrated workflow from the beginning, means the liquid handling system, to the end, which is the analytical part. So the standardization also is within the workflow itself. We have a concept of a modular workflow. So there are 3 modules for each molecule that we test. And in the first module, we test for the most critical attribute, that would be the pH. And that means that we test for a defined pH range from 4 to 7.6 in our case. And we have the stress conditions that I already mentioned, so freeze-thaw, mechanical, and temperature, which kind of reflects the life cycle of the drug product. And at the end, the output would be an optimal pH range or an optimal pH. And that is the input into the second module. At that defined pH, we test several buffer systems. Of course, they are dependent on the pH because you have at different pHs different buffer systems. We test stabilizers, surfactant, salt, and antioxidant, the same stress conditions with adding also silicon oil. And there we have then at the end the optimal composition, which we use for the third module, which is the robustness screening, kind of a DOE approach, where we test outside of the predefined formulation 10 to 20% of the upper and lower range of the definition that we main. And that is defining the formulation design space. So from a lab perspective, we have for module 1 a completely fixed plate layout. So that is the same for all molecules. Then we have in the module 2, We call that a standardized plate layout, as it has the same structure, but of course with the different buffer systems that are possible, the plate layout might look a little bit different if, for example, there are 2 or 3 buffer systems possible. And the DOE approach in module 3 has the highest flexibility. There we really have a DOE defined plate layout. If we have a closer look at one of those modules, we have shown here for the module 1 the plate preparation. So here is the drug substance in the different pHs. We put that into the liquid handling system, and then a master plate is made. That master plate is used then for part of the T0 analytics. From that master plate, we have then daughter plates, and that is an important part for the workflow, that we have then 5 distinct daughter plates that are generated, and each daughter plate has then a distinct stress. For example, if we stick with A1, this A1 plate is then sent into the freeze-thaw stress, and after the freeze-thaw stress, we have then the analytical part. So there, all the analytics is done. The same is true for the mechanical stress. And of course, for the temperature stress, it's a little bit more complicated, as we have different incubation periods. You can imagine that the stress with 40 degrees Celsius is much higher compared to the stress with the 5 degrees Celsius. So we have then, for example, the shortest incubation period is 7 days for the 40 degrees Celsius, and the longest incubation period for the 5 degrees Celsius is 84 days. And as I said, that is fully automated. So when the plate is prepared, each of the temperature plate is inserted into the cytomat, and after the according time, it's removed from the cytomat and analyzed. And then after the analysis, it's put back into the cytomat for the second time point. So for each temperature, we have different time points and several time points. So if we take a broader view on the workflow that we perform, so we have then, as I said, our automation line. But if one thinks of automation, they usually just think about the hardware, but it's really, there are several other key elements that are important if you really want to have a successful automation. So one part, we already touched that, is the workflow standardization. That is extremely important. Then the miniaturization, maybe 1 or 2 sentences to that. In the past, before we had everything on the well plate, using approximately 6 grams of compound, we used syringes or even some tests in bottles with several 100 milliliter or even up to 1 liter bottles. And with that, of course, the drug substance consumption was much higher. And on the other hand, the pipeline dictated that for newer and more fancy and more complicated formats, you don't have that yield, so you need to reduce the amount of material. The other part that we already touched is the automation itself. So of course, it's important to carefully plan the automation, the equipment, and what you need for that. And then, of course, that will be the main topic today is the data management, because in the past, of course, we had only a few data points. And just to make that clear for each module. So metadata and the analytical data, we have approximately, I don't know, approximately around 30,000 data points for each module. And we have, of course, several modules per year. So the data management is important as you have much more data. Then, of course, the data evaluation is as important. And at the end, if you have a clever data management, data science, or the more fancy predictive analytics and machine learning should or is intended to be possible. So let's come to the data handling. So these are some requirements that we defined for our data management strategy. So the first part is that we wanted to have an automated data flow that should start at the experimental setup, covering the data generation, the data capture, and as that is very important, the relevant metadata. Beside that, the data integrity, especially the data lineage, you already can imagine that from the experimental setup because that is the beginning until the data evaluation and data capture at the end. Beside that, we realized with additional methods that we include on a regular basis that we also need a flexible data model that should include the data processing and curation, and it should be capable of continuous improvement. So our strategy is defined in several layers. So we will touch each of them. So the first and the most general part is the data management document. In that document, we define the scope and more or less what should be covered and the knowledge that we have that is then transferred into programming code that is documented and versioned in a GitHub repository. And that code is then used in our Hadoop environment. We have a Cloudera environment, and there we have then automatically triggered jobs that use that code in the GitHub repository. We use the Data Science Workbench for that. And then we have a tool called Navigator that automatically triggers the data governance along the whole process. And we have then a data warehouse called Hive that really has the data storage within the Hadoop cluster. And attached to that, we have then a visualization tool, in our case, Spotfire, and we do data evaluation within the cluster. And on the other hand, we have the option to download data so that we can process them with external tool of choice. So we will start with the data management policy. So as I already mentioned, there the scope is defined, the business knowledge, and especially the rules of data processing. And there is also included in which range methods or data points based on the method are valid, because maybe a method is not valid below or above some defined or tested values. Then, of course, we also define the data quality. That is, I did not mention that till now. We are working under GSP as we are kind of the last part of GSP in the drug product development. So, of course, then the data utility, the data security, where everything is stored and how it's secured, then the data integration requirement of all the different analytics, and of course a data dictionary, data glossary, and some sentences about the master data management, as you will see that, use a few systems for that. So the data entry, or the front end for the user, is our self-developed HTS Studio. HTS Studio, as you can see already on that small picture, has several small applications for different purposes. We also will come to that. At this point, I would just touch the well plate planner. With the well plate planner, for example, you define each well composition, and that data is already the metadata core for all the analytical data that are generated along the process. And also those data, I mentioned that we are in the transition phase, so some data are generated manually and some are generated automated. So for the manual, you can manually upload them also with the HTS Studio, and at the end, from a user perspective, you just see the screening result and have the visualization. So for them, it's just using the HTS Studio, upload everything, and at the end, you just open the browser and have your screening result. And of course, that is important. We log everything that is done, so every manual action and also the automated scripts are logged within the system. So this would be then the process flow. Maybe we focus on the local user for a moment. I already said that we upload everything via the HTS Studio. And what will happen then is that with the upload, we trigger a script within the Cloudera environment. This is the file system, and this is the database. And so the upload triggers the process that a defined script processing is done. And for that, the newest code is taken directly from the GitHub repository. So no code is in the Cloudera itself. It directly takes it from the repository. And then the data table, the pre-processed data table, is stored in the data warehouse. And that data warehouse, as I mentioned, is directly connected to the visualization tool. So the user can directly, a few minutes, 2-3 minutes after the upload, open the visualization tool and see the data points. Beside that, it's also possible to just pull the whole data set, as I mentioned, and export it, for example, for statistics in a different tool, for example, Minitab. But of course, you can also process it with, let's say, the data science workbench, for example, within the cluster. In our data handling process, we have, as I already mentioned, the pre-processing that is defined in the data management policy or document. But beside that, some things might happen during the manual intervention or during the manual processing, and also maybe during the automation, you potentially run into errors. And that is handled with the drop planner, to which we will come in 2 to 3 slides. So you can add flags to data points and potentially exclude them with that via the drop planner. Beside that, as I said, everything is stored, or the whole processing is stored in the GitHub repository. So our documentation in the ELN, in the e-workbook, is then done for the manual process and also the automated process. But for the data handling part of things, we just have a reference to the GitHub repository about the processing. and we have attached the final data table at the end as well in the electronic lab notebook, but we will also come to that. So let's focus on some scenarios that might happen. So let's imagine the scenario that something went wrong with an analytical result, and because of that, you need to redo that experiment and you need to re-upload again, or a second, or a third, or even a fourth time, as an example. What would happen then? So we integrated in the HTS Studio that all uploads are logged, the old ones and the new, and all of them are available. So all historical data are available, and you can see who, when, why uploaded the additional data sets. But the important thing is that always the newest upload is in the final data table at the end. But nevertheless, you logged everything beside that. Another thing I mentioned already is the drop planner, and that enables flagging data values that are invalid. And for that, we predefined standard reasons. So just an example would be out of range or machine error. And that drop reason and additional information, so who, when, why, dropped something, are logged. And at the end, in the final data table, you see then, of course, that it's dropped with a valid and invalid status, but nevertheless, you have the metadata field with an explanation who did it, why, when, and with which conclusion. And as I already mentioned, we are using several systems. So we have on the one hand the ELN, where we do the documentation, and we have some other tools like the GitHub repository for the code and the data that is stored in the Hadoop environment. So it is important that the processing code is really only in the GitHub repository. So we have it only once, and it's referenced into the ELN and also into the Hadoop environments. All analytical data, on the other hand, are stored in the Hadoop cluster, and the final data table, so kind of the output of that, and the visualizations that are the output from the Spotfire are attached to the ELN and signed from two people, so the actioner and the reviewer. And these files that are checked in the ELN are used for the development report at the end. So for each module that we perform, we write a development report at the end. And if we have to change something on the data, as I said, after we finished the ELN documentation or the report, we defined a process and a decision tree in that data integrity document, how to adapt in case of an error or change, so that we only have changes in the Cloudera environment if we beforehand remove the old version in the ELN workbook, or let's say add the new version as well into the ELN notebook. Not that the ELN and the data or the code is not in sync anymore, to prevent that. Okay, so at the end, if we perform that for each module and each molecule, then of course at the end we have a standardized data table, and it's possible to have, we call them all screening visualizations, where you have then a feeling about one molecule type or one stress type, or how the standards, the references perform. At the end, we generate more or less institutional knowledge, which can be used then for further data analysis and, of course, for improvements of the whole process. And that with the process, I mean the methods, the experiments, the workflow, and potentially the automation workflow itself. And that is coming into the topic intelligent automation. So what we understand with intelligent automation is really adapt the process and optimize the process with the data that we generate. So maybe one step back, we chose the Hadoop environment by purpose, as it's a big data solution. So it's an open source framework. It has the data lake concept, so you can add all the different data. Of course, you need to find things, an ontology and a metadata standard. But on the other hand, you have really the advantage with the tool that you have. You are prepared for volume, velocity, variety, and veracity, and to kind of condense that, you have the advantage with such a tool that you have what I described. You have fed all the data into the data lake, and there you have the classical path of a data pump, a data model, and the data warehouse. And at the end, you really have a standardized and predefined workflow. And that, of course, is automated, fast, and at the end, you really have a structured data table for the report. On the other hand, within the data platform Hadoop, you also have the possibility to dig into the data that are there based on the metadata and do then data science, predictive analytics, data mining, visualize whatever you want to have. And of course, that is time consuming and very exploratory. But on the other hand, it really increases knowledge and improvement, and that would also improve and adapt the standardized part. So if in the exploratory part you find something interesting, then you would feed that back into the standardized data path. And that leads to the classical crisp DM cycle. That is that, of course, you have a business understanding, changing research question, and that leads also to data understanding. And of course, those both, so the business understanding and the data understanding is closely linked to each other. But based on that, you do the data preparation, you do then a modeling, in our case, do data mining, for example, and then retrieve maybe predictive analytics. The idea would be that we maybe can predict some parameters so that we can reduce the effort of experiments. Of course, pattern recognition would go in the direction of data mining. And if we talk about a predictive analytics model, we would include that then into the data evaluation and deploy that to improve the workflow, as I already mentioned. So really use real world knowledge to improve the process. So really learn from the data that you generate. And of course, that would help in several fields. Just as an example, with predictive analytics, we work on that. So I have a PhD student who is working in that predictive analytics area. So that with data that are already available along the pipeline, we might be able to predict the pH, for example, that could potentially remove then a whole module 1, or predict something like monomer content for a given formulation. On the other hand, as I already mentioned, data-driven science, it's very interesting to correlate things that we generated over several projects and molecules with data that are generated from a pipeline perspective before or after our work, our group. And on the other hand, machine learning would also be interesting as it's using statistical technologies. Statistics is something that we use as well in our reports. So the classical one, to really learn with the data without being explicitly programmed, so that you can group molecules based on features or clusters. And at the end, the vision, I mean, for time reasons, I don't really go into detail into that. The idea would be then to do an in silico formulation development. Of course, at the beginning, it will be an in silico supported formulation development. So to summarize that, what we implemented is, on the one hand, the standardized part of things, so the screening support, where we introduced the HTS Studio, and I mentioned that the automated data integrity with a lot of data logging. And maybe also there, 2 to 3 sentences as an outlook. That is one reason why we chose the Hadoop cluster, is that we also integrate log files from the automation line, so that we can automatically screen and use those log files for error detection, or also maybe for improvements of the whole automation line. And at the end, what we would like to achieve is having then metadata that are kind of the formulation composition, additional metadata of the process, so how the process was performed, which is also essential. When you do it manually, you usually have a manual ELN documentation from the person who did it. If that person doesn't really exist, especially in our case when the automation line is running day and night, so that, for example, some plate handling is done Sunday night, 2 a.m., for example, there, of course, is nobody there, then it's essential to use also the automation logs for data integrity, because if some data points look maybe strange, you have then the possibility to dig deeper into what happened based on the log files. And of course, then you are in kind of an unstructured fashion, and also for that, the Hadoop environment is made. So you don't really need only relational databases or structured databases. And the other part that I mentioned is the data science part of things, so that you use the data to rank and generate decision trees or do correlation analysis, as you can see on the right. And at the end, as I said, the vision or the ideal state that we want to achieve someday would be supported formulation development. And of course, for that, we would need the data that we generate right now as a learning data set. So the idea would be that a new compound is then used in the in silico formulation algorithm. And with that, we have then the decision based on the algorithm if it's a bad formulation or a good formulation. And on the other hand, you would do the vet chemistry, so the automation run, the experiment, and compare then the result of the prediction and optimize the algorithm with that. And as I said, a PhD student is working on that. So with that, I'm finished, and I think we would have time for several questions.
Thank you, Jonas. That was a fantastic presentation. I really appreciate you stepping forward and presenting the new ideas. There are a couple questions in the chat window. One is, could one station be working on multiple compounds or products at any one time? And especially as some data is needed at lengthy time points, can you then add a new product to that station?
Yeah, so that is actually extremely complicated. What our idea was to, the easiest way would be to, as I mentioned, some instruments can be used manually as well. And so the idea could be to just remove an instrument for a manual experiment that you do beside the automation process or the automation module. That, of course, is kind of the easier or the easiest way. The other way is that in a longer thermal incubation, I mentioned 84 days, you already start the first part of a second module. So we are working on that. That is also linked to the log files, how to optimize that. We collaborate with the Fraunhofer Institute for Automation, that is a governmental founded and supported institute. And they have some experience in that, but nevertheless, it's still a complicated task, but we are aiming for that.
All right, there is another question, a clarifying question really. So dropping data points is by human decision, is that correct?
Yeah.
I think on slide 18 you were talking about making that decision from the raw data into that, which data points we're dropping. It is a human decision, and how is that captured?
So maybe a few sentences as an explanation. So when we have, so the first thing is the pre-processing. That is kind of based on decision trees that are defined in the document and also in the code. And then we sit together as a whole group, having Spotfire open, and have in the manual way, or in the manual case, we have then a document where we describe all the things that happened during the processing and which might affect some data points. On the other hand, if we have an automated screening, we would have then a condensation of the log file, what happened during the screening. And then we have, as I said, the drop planner, which we use as a group. And based on the findings that we have along the process, we look at the data points and then we decide in kind of a risk evaluation of what happened, if that data point needs to be excluded or not. And if we decide that it's excluded, then we choose a predefined and standardized kind of explanation for that, or from our perspective, that defines the root cause why it should be dropped. And with that, then this particular data point gets a flag. It's not deleted or anything. It just gets the flag that from our perspective, it's dropped. And of course, the reason why we think that it should be dropped is also tracked in the database. And at the end, when you have a look at the data with visualization tools like Spotfire, for example, you of course can, for the the data set that you want to visualize, of course, you can include dropped samples. You can have a screening of the dropped samples, how many samples, why were they excluded? And on the other hand, of course, you can just have a look at the analytical data that are not dropped and then potentially used for the statistical evaluation. So it's more or less absolutely clear if one data point is kind of missing, why it's missing, and what was the reason or the conclusion why it was excluded. And of course, that is not, of course, we don't have reasons like it's not really fitting into what we expect. It's rather we had an error with the machine or something like that.
Yeah, but the data itself is always captured. It's traceable from the raw data all the way through.
Yeah.
Yeah. Fantastic. Here's another question. For the individual tests, you have bypassed the vendor software using a common vendor neutral code, or is the individual vendor applications integrated into the total solution?
I don't really know if the perspective would be then the automation part of things or the data handling, so I will just cover both. So from an automation perspective, we have a control software that controls all the different vendor softwares, so they are included into that. From a perspective, data-focused perspective, we have kind of a mixed bag. So if a simple method like the plate reader, we just really export the measurement that is really, so the absorption that is measured in the machine, and the processing, so the raw data that come from the instrument, the whole processing is made in our Hadoop environment and tracked there and also logged there from the beginning. And of course, then you have several, as I said, circles of processing based on the method. More complicated is the UHPLC, as we are looking for percent monomer, and of course that is not measured directly in the UHPLC. We are using an algorithm for that, and that is quite complicated. And on the other hand, we don't really want to rebuild all that. So we use the CDS system that is also, by the way, controlled via the automation line. And in that system, that is also documented, we predefined a processing method and a reporting method. And within that method, we already have the processing, so that we really get from the measurement in the UHPLC to, as I already mentioned, a percent monomer, for example. And that percent monomer is condensed in a report, and that report is exported into the Hadoop environment. And based on that, we do then some normalization between the different runs, as we also have the standards included. But to summarize that, we have on the one hand side fully data processing in the Hadoop environment, and on the other hand, if it's really a complicated analysis, we also included the vendor software as well. And the raw data in the case of the liquid chromatography are stored in the CDS system as a data source for the raw data. And only the processed, but not the final process, but the process data are fed into the Hadoop environment. And of course, this is also documented in the ELN. So you have an additional reference to the not only the data in the Hadoop environment, but also the raw data in the CDS system. So to summarize, it's kind of a mixed bag.
Thank you. I think that at this point, this is all the questions we have time for, but I really wanted to thank everybody for attending, and also Jonas, thank you for presenting.
You're welcome.
Going forward, if anybody would like to present on a data integrity topic, please let me know. I've posted my email in the chat window. But with that, we're going to end the meeting. Thank you again for attending, and we look forward to seeing you again soon. Bye-bye.
Bye.